So we're doing policy evaluation in a reinforcement learning framework. And the reason we're doing this is because we're going to see later on that it's going to be useful in some cases to build reinforcement learning algorithms with policy evaluation as a component. We're going to see, for example, when we study policy gradient algorithms later in the class, policy evaluation is used to reduce the variance of policy gradient algorithms. So that's one place where it's directly used. We're also going to see where effectively we're going to use policy evaluation to get a Q function. And then we can directly, effectively use policy evaluation in an optimization setup. So basically, and also the classes of policy evaluation algorithms that we're going to look at just have direct analogs in policy optimization. It's like we're just going to turn, well, just running the policy, selecting the action according to the policy, to selecting an action according to an explore-exploit policy. That's the only change. So while this may not be as interesting from an application perspective, you're going to be learning the basic principles that are important. And last time we pretty much finished up with the Monte Carlo approach to policy evaluation, which was extremely simple conceptually, right? So what you get as data is these runs of the policy. This is showing the states, and in this case, all the rewards are 0 except for the final reward of 1 or -1. And we said, well, to estimate the value of state 1,1, we're just going to average the returns that we got. And the pseudocode for that looks something like this. So you generate a trajectory, and then you basically sum up all of the, so for state S of t, you're going to compute the future to-go reward. And if we remember, that's just the reward, discounted reward from time t onward. And then it's effectively just averaged all of those for each state. And in this case, we were just looking at the first time a state occurs in a sequence. We only consider it once. You can consider it multiple times. The analysis of that algorithm is a little more complicated. And we said that this will work in the limit because in the limit, averages converge to expectations. Ultimately, that's why this works. It's the law of large numbers. And then we went on to look at, well, how many trajectories do you need to get an accurate Monte Carlo estimate? And I won't go through all those details, but we basically introduced the turn-off bound, which is something that's well beyond this class, is a useful tool to have. It's used all the time in theoretical computer science and statistics. These are sort of uniform convergence type bounds. They're used often in that context. But what we found was a way, so W was the number of trajectories that we were going to use to estimate the value of state S. So the number of examples you had of state S and then the policy. And we showed that, well, with probability at least 1 minus delta, so delta is going to be a small thing usually, we will have this bound on the error. And this kind of made sense. We see that as W increases, the number of trajectories increases, the error goes down. That's obviously what you want. As delta gets small, this thing gets larger, and that makes sense because as delta is small, that means that you have a higher and higher probability of this bound being satisfied. So this gives you some sense that the algorithm converges very quickly.
I have a question on the concept. From the equation, it seems like if we just downscale all the rewards, then our Rmax value will reduce. So that would reduce the number of tries?
Well, it will reduce the error here, and yeah. So if you want, so often there's going to be a relationship between the error that you're looking for So usually say, okay, I want to have an epsilon error, at all this, no more than epsilon error at all the states. And then you would have to set this thing here to be less than epsilon. And if you know your domain has very small rewards, you'd probably choose a smaller epsilon. And so you might scale it anyway on yourself. But you're right. To get the same epsilon error, if all the rewards are scaled down, then you don't need as many trajectories. Yeah, and that's just the nature of things. When you have larger values that could occur, you have to sort of have more samples because there could be a low probability of those occurring. Yet when they do occur, it has a big influence on the mean. Yeah. So any other questions? Okay. So this was a tool that we introduced, and so this is where we ended last time. We said, yeah, Monte Carlo is nice because it has strong convergence guarantees. Like it'll work if you run it long enough. There's no question about that. This is kind of a computational thing. You got to wait till the end of an episode, and there also has to be a notion of episode. You can't be running forever, right? You could imagine RL tasks that are just continuous, and there's no real notion of like an episode ending. You're in a network traffic application where you're just serving packets, and you're just doing that your whole life, and you want to optimize or learn the value of a policy. But the bigger thing is that Monte Carlo is kind of a black box approach. Like it does not care that these values that we're averaging are a result of running a policy and a Markov decision process. Like you could just give it random values and it's going to average them, and it does not do anything to think about the fact that these are a sum of rewards over time in a Markov decision process. Right? It treats the return to go, that GT function, as just a number that has no structure at all. It's just averaging these numbers. So basically, Monte Carlo does not exploit a lot of information that we do have, right? It doesn't exploit for every one of these samples trajectories that we know what the states are, right? We know what the actions were, and we know what the individual's rewards were at each time. It just does a big sum. And so we'd like to exploit that. It feels like if we take that into account, maybe we could do a little better. And that's what we're going to look at now. And specifically, one of the main things we're not taking into account is that this value function for a policy, we know that if this is an MDP, it must satisfy this equation. Right? This is the value function equation for a policy. All policies will satisfy this. Monte Carlo estimates don't care about satisfying that. Right? They're never really going to satisfy it. They'll approach satisfying it, but they'll never actually satisfy it. So if you believe that this is true, why not try to exploit it and have an estimation procedure that takes it into account and doesn't consider all these other functions necessarily that don't satisfy this? So that's what we're going to look at now, different ways of doing this. So the first way is really simple. Like there's not too much to think about here. So the model-based evaluation is just to learn the transition and reward function. So this is basically just model-based RL, right? And then you get all the data, you estimate the transition and reward function for that policy, and then you solve these equations, right? That's kind of a no-brainer. That's basically what model-based RL is, except here we're just using it to evaluate a policy. So nothing really to think about there, nothing new. You could say that this is going to be expensive and it's not going to scale for really large MDPs. And at the end of the day, when we get to reinforcement learning with function approximation, there's no nice way to sort of generalize this to the domain of function approximation, right? So because ultimately this is about solving a matrix equation. So we're going to look at something else, something that is going to be computationally less expensive it's going to avoid trying to explicitly learn the model in this case. And this is called temporal difference learning. It's one of the It's sort of the other class of algorithms compared to Monte Carlo when we talk about sort of value-based reinforcement learning algorithms. So value-based reinforcement learning algorithms are always trying to learn value functions, where Q functions are an example of value functions. And these are the two classes of value-based methods, Monte Carlo and TD. And so now let's see what temporal difference learning is. It's a pretty interesting idea. It doesn't require learning a matrix of transitions. It's just going to maintain a value function vector, and it's going to iterate that vector with each experience. So this is the algorithm. So I'm just going to show you the algorithm first. We'll go through it. You'll see it's a really simple thing. You can implement this in a few lines of code. And then we're going to try to understand why this makes sense. So all the algorithm's going to do is, and this is really just looping over episodes. So every episode you start in your initial state, and then for each episode you're just going to keep taking the actions of the policy. Remember, this is policy evaluation. Every time you're going to see the reward in the next state that you got. Right? So that's all really easy to do. And you could all do this. You could all implement this today with the machinery we gave you in the last homework assignment in 10 minutes probably. And then you're going to be maintaining this value function vector. So there's a component in the vector for every state. And this is the update you do. You're going to say, okay, my new value is going to be updated to, well, whatever the old one was, plus this is going to be a learning rate and this term here. Right? So this is all there is to it. Really easy to implement. And now let's look a little more into why this update makes sense. So first, any questions about just the mechanics of this update? Right? It's pretty straightforward. So we're looking at the pieces here, and it looks a little this is kind of a circular type of learning algorithm, but so is the Bellman equation. You've got values on both sides. So these are just the current estimates that we have. This is a learning rate, this is an observed reward, and this is your update. And intuitively, what this is going to do is it's going to move us closer to satisfying the Bellman equation. This is the Bellman equation. You can see there's kind of a similarity, like reward plus value at S prime, reward plus value at S prime, minus our current estimate. So we're going to see why this kind of makes sense now. But it's related to the fact, it's basically derived from the fact that we have this Bellman equation constraint. So before we do that, I think it's useful to look at maybe a simpler case, and we'll see that this case is very related to the temporal difference learning case. But so this is kind of an aside, but it's going to build some intuition, I hope. So let's say you want to incrementally maintain the mean of a sequence of numbers that's coming in. So you get a stream of numbers coming in, x1 through xn, just real numbers, and you just want to at all times have the mean maintained of those numbers, right? That seems pretty easy, right? So one thing you would not want to do is store all the numbers in a big array, and then like every time you add a new number, compute the mean of all those numbers, right? That would be kind of stupid. Right? You'd all immediately see, okay, I can do something better than this, and I probably don't even have to store all the numbers, right? We don't want to store all the numbers because you want something that just can stay online forever, maintaining the mean. And so you could all figure this out, but I'll write down we'll go through the equations. So this is the average of n plus 1 samples, and that's equal to this, right? Nothing fancy there. You just average all the values, and this would be the stupid way to do it if you were storing all the values and you got your n plus 1 element. you can rewrite that, just using a little algebra. You can rewrite it in terms of the old mean, right? This is the mean from that you had before you saw the n plus 1 value, and plus this term here. And you can go through the math, and it's just a little manipulation of everything to make this work out. And so that equals basically the old mean plus this new thing. And you can see there's a very similar form, we'll see this in a second, to the TD update. So we're going to think of this thing as a learning rate, right? 1 over n plus 1, and it's a learning rate that tends to decrease over time. That tends to be what you have to do for these types of learning rate algorithms to make them work theoretically. This has a particular way of decreasing over time. And this is your new sample, right? This is the new data you just observed. And then this is your old estimate. And it's saying, okay, is my new sample close to the current estimate? And let's say the new sample is exactly the same as the current estimate. You're not going to change anything, right? This is going to be 0, and your next estimate is the same as the current estimate. If this new sample is really far away from the current estimate, let's say it's larger, right? You said your current mean is 1, but you observe something that's 100. Well, you're going to move this in the positive direction. You're going to make your new mean estimate larger. So this is all very intuitive, kind of makes sense. And so basically the form we have is your current mean plus a learning rate times the error, right? The error that you get, sort of an instantaneous error you get with a new observation. And that's what that text says. So that's online mean estimation. Very simple, but basically that's what the TD update is. So this is our current estimate of the value, and we can think of this as really a mean of a whole bunch of returns, right? That the value function is an expected value. And so it's our current estimate. This is our current estimate, right? This is the updated estimate. And the current estimate plus a learning rate. This is something we're going to think of as a noisy sample of the value. Okay? This is a noisy sample of what we would like our value to be. And then this is our current value. Okay? So this has the same form as before, except before we just had some number come in, and that told us, that was the new data, that told us what we would like our mean to move towards. And now we're saying we're going to use this as the thing that we want to move our value towards. And we have to figure out why this actually makes sense. Does this make sense? Does anybody have an idea of why this might make sense as something you would like to move your value towards? Right? This is kind of serving as a noisy estimate of the value of VS. Why would that make sense? Right? I was in state S, right? I took the policy action and I saw a reward, and then I know what the value function estimate is in that next state. Let's assume that we had the perfect value function estimate at S prime, right? That's the next state. Let's assume it's a deterministic reward function. This would be very close. This is very close to a sample of, a sample of the value function here. So I'm going to try to build a little more intuition into why this makes sense. And this is a lot of text here, but the point of this slide is basically that most reinforcement learning algorithms, you don't have to read all the text. Most reinforcement learning algorithms can be value-based ones can be viewed as starting with some, I'm calling it a dynamic programming algorithm. Like value iteration, we think of that as dynamic programming. You start with that, and then you basically realize, okay, dynamic programming is doing a whole bunch of little expectation computations, right? You're computing an expectation over the next states, for example. And a lot of RL algorithms can be viewed as just simply replacing the expectation with a sample. Right? You sample one of the next states as opposed to considering all next states and weighing their probabilities. And so let's see what that makes. Let's see what this looks like. So what I'm showing here. So if you remember when we were doing value iteration, we talked about an iterative policy evaluation approach, right? Where we said, okay, you can just restrict all the actions to only be the ones that the policy returns, and then you do this iteration, and that converges to the value function of the policy. We also said that value iteration can be done asynchronously. You do an update at one state at a time, and it basically will still converge. And so this is just putting that all together, and it's showing you asynchronous policy evaluation. So you repeat forever, select any state you want. You just have to make sure all of them are considered infinitely often. And then you did a little, this is the analog of the Bellman backup restricted only to that policy action, right? And if you run this forever, it will converge to the value function of the policy. Right, so we okay with that? All right. And what you'll notice, so why can't we do this in a reinforcement learning setting? Like what is it about this algorithm that we can't run? What pieces here do we not know for reinforcement learning?
Transition problem.
Yeah, we don't know this. We also don't know the reward function, right? So basically, in temporal difference learning, we don't have these models. Right? We don't know what R is. We don't know what T is. And so how you can view TD learning is it's sampling. Instead of doing this full expectation for a backup, right? It's not going to do this full expectation. It's just going to get one sample of the next state S prime and the reward. And it's going to move V pi S in the direction of R plus that sample, right? So this is a R plus beta V pi S prime. This is a stochastic estimate of this true expectation here that we can't actually compute. And this is very much like stochastic gradient descent, if you're familiar with that. Like pure gradient descent will sort of do an expectation over all data. When you have a finite data set, it's an expectation of the gradient over all the data in your data set. And stochastic gradient descent might just sample one data point and get a gradient estimate. And this is very much like that. So it's a noisy estimate. And it turns out that if you run this algorithm and you replace this true expectation with noisy estimates based on sampling each time, this will still converge. And it converges. Yeah, so it's more complicated to get into this, but there's a whole theory of convergence of stochastic algorithms. And this will converge with probability 1, which is the most, like the strongest form of convergence pretty much, and to the true value function. So basically, any run of the algorithm is guaranteed to converge to the true value function in the limit. So a very strong notion of convergence. And that's basically what results. That gives you this whole algorithm. So you can view this as doing asynchronous value iteration, where the states that you're selecting to do the updates are just based on running the policy. And asynchronous value iteration is just using a noisy estimate of the next state. Okay? And yeah, it's kind of interesting because these samples are based on our own estimated value function. So it feels kind of like self-serving and like it shouldn't really converge, but it does. right? Because you imagine, well, what if this is really bad? What if our initial estimate is really bad in the beginning? Well, we said for value iteration, regardless of what your initial value function is, it converges. And for the same reason, at the end of the day, this also converges regardless of how your initial value function is initialized. All right, so will it converge? Yes, it does. Non-trivial result, this stuff is not too difficult, but you have to get into stochastic approximation theory. It will converge if a couple of things are true. So the learning rate is the main thing that you have to worry about. And the learning rate has to satisfy these two properties. So the learning rate, I don't have it indexed by update time here, but in general, it has to be indexed by update time. And it has to satisfy these two things. So the sum of the learning rates over the infinite horizon have to sort of blow up. And the sum of the squares of the learning rate have to not blow up. Those are the two conditions. And these are very standard conditions in any sort of algorithm like this that you're gonna play with. And basically, this condition here just effectively tries to make sure that you're not going to have too high variance forever. So it's controlling sort of how much you're going to change things by as time goes on. And this is making sure that you never get too small of a learning rate so that you can't make enough progress to converge. And it's just this tiny trade-off. And there happens to be at least one learning rate that satisfies these equations, and that's using the learning rate of 1 over n. Right? So 1 over n, the infinite series, that does not converge. That's sort of related to the logarithm. And 1 over n squared does converge. So that's like related to pi somehow, right? So yeah, this is a very, very interesting algorithm. I mean, it's a little puzzling because it feels very self-referential, right? You're starting from your own knowledge and you're updating the value based on your own current knowledge. And it feels like, maybe you should just get in some sort of self-serving loop where you think everything's good, but and you just end up converging to that sort of fictitious value, but it doesn't happen. And that's because you do have something real that's coming in here. It's this reward function. And so at the end of the day, you have to be consistent with the value, with the Bellman equation, and this reward that you see every time will force you to get there. So any questions about TD, the TD algorithm? Right? At the end of the day, what we had was this algorithm, which you might as well think of as a form of asynchronous value iteration, but it's a stochastic approximation of that. Right? If we put the restricted Bellman back up here instead of this line, you would have asynchronous value iteration, and everything would work out just fine. Okay, so that's TD. And we're going to be coming back to that more than once. But I think this view of reinforcement learning as being stochastic approximations of these TD-like algorithms and value iteration-like algorithms is a very useful thing to be thinking about. We'll see that classes of reinforcement learning algorithms will come out of that. All right, so not too much to say here. We looked at Monte Carlo. This is kind of model free, but it doesn't use the fact that we're in an MDP. This is model based. It's going to be expensive, harder to generalize, and this is sort of model free. Takes into the account that we have an MDP. It looks at actually the states on the trajectory, and it's called temporal difference learning because it's just looking at the difference between time steps, right? That's really the amazing thing. It's just trying to make the equations consistent across individual time steps, and if you do that enough, it converges. So that's why it's called temporal difference learning. It's trying to get a self-consistent function. All right, so not much to say there beyond what we did, and now we're going to move into optimization, which will be more. This will be what probably the next homework will be based on. So I think the next homework will have you do Q learning and do an asynchronous version of Q learning. That's what we're shooting for now. So we're still going to be in the small state space case, and we're going to focus on value-based methods. And so we just got done with policy evaluation, learning v pi given pi, right? Okay, so that showed us a few principles. Now we want to actually try to optimize the policy. So I'm not going to give you pi anymore. I'm just going to let you run around in the environment and figure out an optimal policy. And so, again, here we're going to have two different ways of learning an optimal policy. One's going to be based on Monte Carlo. One's going to be based on temporal difference learning. And these are going to be very, very analogous to what we just saw, and almost exactly analogous. All right, so to get into it, let's just review model-based RL, because this is we're going to sort of expand on this. So what we did there is we were learning, we were just getting a current policy. We were solving for the current optimal policy given our model. We took an action according to an explore-exploit policy, right? You either do something greedily with some probability or a non-greedy action. And then we updated our model and we solved it, and that's all we did. So now what we're going to do is we're going to replace this step, because this step basically results in a value function. And with a value function and the model, right, we can figure out the one-step look-ahead greedy action and do explore-exploit. So the first TD-based algorithm that we're going to look at for optimization is just going to replace this optimization step with TD. And it's going to look like this. So we're going to start with an initial value function. Then you're going to, take an action using the explore-exploit policy. And this is going to require a model, right? So why do we need a model again? We've talked about this many times. So all we're maintaining is a value function. Can we figure out the greedy action with just a value function? No. We have to do one-step look-ahead, right? And so that's why you need the model. So we estimate our model, and then we perform a TD update on the value function to try to get the value function to converge. So you're not going to be maintaining a model for the purpose of computing the value function. You're going to be maintaining it just so you can compute the greedy policy. All right? And this converges. So if you have a glee exploration function, and you have your learning rate decaying at the right, under the conditions that we looked at, this will converge to an optimal value function. So that's pretty interesting. And this alone is actually, so it may seem that by requiring that we have a model, this is pretty limited, but actually it's not in a lot of cases. So there are plenty of cases where you literally have a model for free. You don't even have to learn it. And so we'll see this when we get to function approximation, but you can very easily create a function approximation version of this algorithm where you're using something like a neural network to represent V instead of a big vector. And for something like a game, Go, or this was originally used for a game called backgammon. This is one of the early successes that we'll see when we talk about function approximation. You already have the model. Like you're given the model for free, and we just don't know what the optimal value function is, and the model is too complicated to actually solve for the value function using planning. And so this actually can be useful. If you have a model already, all you need to do is just keep on doing updates to learn the value function. and you can converge to an optimal policy. All right. So this is TD-based optimization with a model, but you can't get around needing the model because all we're doing is learning the value function here. You have to have the model. Okay, we've already answered that. So yeah, that's it's pretty interesting that can converge, right? Because it's this continuously evolving. There's lots of. We show that this converges for the policy evaluation case, where there's a fixed policy, right? There was a fixed policy. You were always just running a fixed policy and running this algorithm. Now we're running the algorithm, and this policy is continually changing, right? You're basically always running an explore exploit policy, which is always changing because as the value function changes, so does the explore exploit policy, and yet this still converges, right? So these are kind of non-trivial results. The same mathematical machinery that we saw for policy evaluation that's still used here, but it's pretty interesting that these things will still converge, because it seems like everything's just kind of changing all the time, but yet something's driving it to the solution. And what's really driving it is the Bellman constraint underlying everything. And really, if you look at the math behind all this, the contraction property of the Bellman of the MDPs is really what's driving this to converge. Even in the stochastic approximation theory, the contraction property is something they sort of hinge everything on. So you can do a similar thing for Monte Carlo evaluation. So instead of using TD to estimate the value function, you use Monte Carlo to estimate the value function. For some reason, the theoretical convergence of this is harder to analyze, and I don't even think they fully analyzed it. I looked maybe a year ago, and there's still they can analyze some tweaks to that, but they haven't figured out that the Monte Carlo version still works. But yeah, that's a pretty technical point. So yeah, it is worth thinking about this a little bit more, though. Like, why would we expect this thing to work at all, right? Learning from a continually changing policy, like you're trying to learn the value of a continually changing policy, and the policy is based on a continually changing value. Like, it feels like there's this self-recursive thing. Well, one bit of intuition is that we've already seen something like this before. This generalized policy iteration algorithm was doing very much the same thing, right? So generalized policy iteration was saying, okay, at every step, I'm going to pick a state, and then I'm going to either choose to do a Bellman backup or a policy evaluation step of that state, or I'm going to do a policy improvement step. And so in this algorithm as well, since every time you're either choosing, to improve the value function estimate or improve the policy, this is as well at all times it's sort of continually updating the policy and continually updating the value function. And we talked about how this still converges. And so what we just saw was just the stochastic sort of approximation of this in action. All right. So that's what we had. Now, this is unsatisfying because it does require that you have to have the model or you have to learn the model. And it would be nice if we didn't have to do that. So then if you're using a function approximator like a neural network, you could make all of your decisions just with that one neural network and not have to have this model that you're doing one step look ahead for. So we're going to talk about how to do that now. And in particular, we're going to talk about trying to get a TD-based version, kind of like this, that learns a Q function instead of a value function. So if we can directly learn a Q function, then we don't need a model, right? So if I gave you the Q function in a state, how are you going to pick your action? Find the highest value, right? So I'm giving you the Q function. It returns a value for every action. You'll take the highest action value. And so that's what we're going to look at next. And I guess we'll start next time. There's going to be two different versions of the two different main algorithms for learning the Q function. One is going to be called SARSA. So who's heard of SARSA? Right, it's a pretty famous algorithm. And that's going to be based on sort of starting with generalized policy iteration and making it a stochastic approximation of that. The other algorithm is going to be called Q-learning. So who's heard of Q-learning? Right? More people. That's going to be based on starting with value iteration and then making a stochastic approximation. So next time we'll do both of these, and we'll look at the different trade-offs involved. Okay, so I'll see you on Monday.